everyone, this is Shashank. We'll be looking at the kinematics graphs. First thing, this is a simple topic which is very much similar to your graphs and in the coordinate geometry, so which you have been doing in your 10th standard, 11th standard, 12th standard as well. So it's more of a maths topic here. Okay, let's take a case where you have a graph of s versus t to be a straight line here. Now we'll be looking at a lot of combinations of the graphs here, and we'll try to understand the principles that will support this thing, right? So the first thing, when the graph of s versus t is a straight line, what would be the corresponding v versus t, a versus t, right? And which scenario would this graph be true in? Okay, so first thing, we know the interrelations between these variables, right? From s to v, how do I get it? So I have to do the differential here to go from s to v, right? This is ds by dt, and to go from v to a, I'll have to once again differentiate. This is dv by dt, correct? So I know that this differential is nothing but there's another name for differential. Okay, what is that? Yes, it's the slope. Now, whenever I have a variable s varying with t, it also means that the slope of s versus t is your velocity here. So, for example, if I have a line which is represented by the equation y equals to mx plus c, right? So we know that the value m there is the slope here, right? Y equals to mx plus c, the m here represents the slope, which is the same here. So it's a straight line. We know that for a straight line the m is constant, which means the slope is constant. So for this graph here s versus t, the slope is a constant value. Now which means that slope is what I'm calling it as velocity, right? So the velocity versus time graph will be a constant here, a straight line parallel to x-axis. That's a constant here. What about a versus t? A value which is constant has got zero slope, right? So the slope here is zero. Therefore the a versus t is a graph which is a zero value. We know that from the law of Newton's first law of motion, the force acted upon an object moving with uniform velocity is zero, right? As per that definition, we can substantiate A equals to zero. Similarly, in such a case, the displacement s is given as v into t. Or in other words, it's a graph which is a straight line having a constant slope. Now there are a few versions of it. It could be that the initial displacement of the particle is a non-zero value, which means it's already starting from uh, from a certain displacement, right? As per which is not our origin. It's not directly starting from the origin. We could have a graph that is parallel to this, which is like this, having the same velocity. Even even the velocity time graph of such a s versus t would be the same, because these two have got the same slopes. Remember, this varying c only slides the line up and down the axis here, right? Now let's look at another case. Let's look at a case where the acceleration is constant. So this is the motion of an object under constant acceleration. So your a versus t is a constant straight line, right? So now we're going to do the other exercise, which is trying to get from here to here, right? So we know a line which has got a, so when the slope is constant, we know that the graph is supposed to be a straight line. So the v versus t is supposed to be a straight line which is either going like this with a positive slope, right? A line which has got a positive slope, because a is positive here. This is your graph of v versus t, isn't it? Now, how would the s versus t be for such a graph? The s versus t, now once again we can see here that the velocity is increasing, which means the slope of this graph has to keep on increasing. So such a graph with a constant with a positive acceleration would look something like this, where at each and every point the slope of the curve is increasing. So in this sense, we know that the displacement of an object moving under constant acceleration would be given by ut plus half at square. We have already derived that from the kinematics, and therefore we can substantiate that it's going to be a parabolic equation. Now let us see this other case where the acceleration is negative. How would you imagine that curve being? Right, when the acceleration is negative, the same a versus t, which is a constant, but just it is below the y-axis. It's a versus t, but it's below the y-axis, which shows that it's a negative value. So when the a versus t is negative, that shows the slope is constant but a negative value, which means the velocity versus time happens to be a curve which has a negative slope, and the graph could be a value which goes like this, which has got a negative slope and a straight line. Example, when we have an object that has been projected up but has got a decreasing velocity due to a negative acceleration of gravity, and in such a case, how would your s versus t look? So the slope of s versus t happens to be reducing. So the graph would look something like this, because the slope at each and every point here is reducing slowly, because the slope is represented by velocity v here, whose value is a reducing value. The slope corresponding to each and every point on these curves can be obtained by just taking the tangent at this point here. As we draw the tangent at other points, we can understand that this slope is increasing as you go ahead in time. That is what is being represented by this v versus t graph, as you notice the slope being increasing from time to time. Now in the same way, if we draw the tangent at this point and if you draw the tangent at this point, we can notice the slope of these lines is reducing. That is what is being represented by the line that's drawn here, which is basically the slope, the values of the slope at various points of this curve. So let's take this understanding in applying it for a simple example problem here. As we know from the last part of the graph, which tells us that the motion of an object thrown upwards in uniform gravity has to be a v versus t represented like this, right? Let's use this knowledge here and find out certain things. For example, you would know for an object that's projected vertically up, we know it goes to a maximum height h and then it returns back due to gravity, which is constantly acting downwards. Now for this motion, we know the time of flight represented by the time of ascent plus the time of descent, right? So most of you already know that this time of ascent and time of descent are both equal, right? So not only that, we also know that the object, when it comes back to this point, its velocity would be the same u in the downward direction, right? Now let's have a simple proof of these two facts using the graphical method. Now let's consider this is the u versus t graph here of this object. Initial velocity at t equals to 0 is its speed u, and as you know, it would go a certain time here, and then its velocity would become 0, which is at the topmost point. So that is represented by this value here. The velocity is 0, and therefore this would be your time of ascent ta, after which the object is going to return back downwards, and at the time taken by it to reach the final point here would be given by the td, right, which is the time of descent. So at this point, we are bringing up another very important characteristic of these graphs. That is, wherever you have the v versus t, we know that the slope of s versus t is v, the slope of v versus t is a, and at the same time, the area under a versus t is your v, and the area under v versus t is your displacement s, right? So for example, the area under a versus t graph here would be your value of velocity v, right? This area would be equal to the value of velocity at this point of time, which is this value here. Now similarly, the area of V versus T would be your displacement S. This area would be your displacement S, which is the value here at this point of time. For the time 0 to TA, the area under the graph here should be equal to the displacement of the object, which is nothing but the height h. Now let's consider the other motion from the topmost point to the bottommost point here. So while the object returns from this point to this point, even then the object is going to travel the same distance h, which means now if we consider in this graph, from the topmost point where the velocity is 0 to the bottommost point, which is characterized by this value td, the time of descent, the area under this v versus t should be equal to your displacement. And since the magnitude of the displacement is the same, which is h here, the same will be the value of the area here, which will be h. Now this suggests that these two triangles here, and these two triangles are similar triangles for the simple reason this angle is the same as this angle. This is 90 here, this is 90 here, which suggests that this angle and this angle are both same. So these two are similar triangles and they've got the same area, which means they are also congruent. Now these two triangles are congruent, which means the sides would be of the same length, right? So this TA here should be the same as this value TD. So from the graph we can say therefore that the time of ascent is supposed to be equal to the time of descent, right? At the same time we can also say that the velocity of the object when it returns back is supposed to be equal to the same value u, because for the simple reason here this length should be the same as this length. Since this length is u, this length will also be u. So this object is going to return backwards with the same speed u in the backward direction. Now let's take another question, and a very interesting question, which we'll try to solve from this knowledge. So at any point on its path, the body will have same speed for upward journey and downward journey, right? Which is something we have just before discussed, right? It's an extension of the statement we just before discussed. That is, we said at the bottommost point the velocity u would be the same as it was when it was thrown up. When it returns down, it would be the same. Now this bottom is never a fixed place, right? You could change the bottom to be at any point of its path. So therefore at each and every point you could apply the same and say at every point on its path the speed upward and the speed downward would be the same. It would very well be true, yes. If a body thrown upwards crosses a point in time t1 and t2 respectively, then height of the point h is half g t1 t2. Now let's solve this from the equation of graphs. The question states if you have an object thrown upwards which crosses a certain, let's say a height h here, at the first instance t1, and let's say as it goes up it returns back once again, and as it returns back, let's say it crosses it one more time here, which is at t2. Okay, so let's understand this when the time when the mass crosses this particular height. The first time it crosses is t1, and it goes up to the top, then comes back down here. So the second time it crosses here is at time t2. Alright, so now let us try to represent this in a graph. See, the first part, it has started here with a speed u at t equals to 0, and the object keeps moving forward. So the first time it crosses this height h, right, this height, it reaches this height at time t1. So let's say this is time t1. So in time t1, now if we calculate the value of the area here, as we know, the area of displacement versus the area of velocity versus time graph is supposed to be displacement. V versus t, area is supposed to be displacement. So therefore we know that here at this point this value of displacement should be equal to h, because the object's displacement from this position is h, and at time t1 we have this particular, at this position we have the displacement h. So now the question is, let's first try to understand the times here. So this is time t1. Now from the same point this would go up and then reach the same point while returning down. So let's say that happens at time t2, right? So the interesting thing is, let's say here, look at this arrow here. This points to the time where it reaches the where it reaches this position here. You see, now as we have discussed before, you in this particular graph, this triangle, if you say this is triangle OAB and triangle AO dash B dash. So triangle OAB is supposed to be semi-congruent, right, to triangle AO dash B dash. And now let's say the displacement h happens at this position, which is characterized by, this is another point here P, let's say, and this is Q. So triangle AQP would also be, if at all you want to find the total displacement of this particle when it reaches this at time t2, the total displacement would be also h. Why? Because this object has gone from this position to this position, so the displacement should be h. It doesn't matter the object is returning down, right? Because we are not talking of the velocity here. So therefore, now if I have to look, if you consider this graph at time t2, what is its total displacement? So if you notice here, you can understand that since pq should be the same as the, let's say this is p dash, I'm sorry, let's say this is q dash p dash a. So apq should be identical to aq dash p dash, because as we have seen here that these two are congruent triangles, and we know at this position the speeds of the particles are supposed to be same, right? By that logic, I'm going to say the value of this remaining leftover displacement should be the same as h, because when you add the respective areas, when you want to calculate the total displacement at time t2, you're going to add this area. Let's represent that area with right, with another value a1. Let's say that is a1 here, and this area is a2 here, and this area is a3 here. Now the equation that we have essentially is that a1 plus a2 plus a3 should be equal to the total displacement of the particle, which is h, right? Now you can see here a2 and a3 are going to be equal and opposite, so they're both going to cancel out each other. So a1 is supposed to be equals to h, which means, you know, when this is h, we know that from the total triangle area, which is the exact same as this, if you have cancelled out a3, you know that basically a1 should be the same as this area here, a1, but it's just minus, it's just in the negative direction, right? So this is the only equation by which the displacement will be same, equals to h, which means a2 should be the same as a3. So by this logic we can say that if this total time is t2, and you know, now since this area is the same as this area, this value which is t1 should be the same as this value here t1, which means, you see, the total time of flight, which is the total distance from total time from here to here, should be equal to t1 plus t2. You can see here this is t2 and this is t1, so t1 plus t2 should be equal to your total time of flight, right? So because it is t1 plus t2, so now because this initial time is t1, the rest of the time should be equal to t2, okay, which means, let's say the particle crosses this height h at two given times t1 and at another time t2, which is you know, the same in the same line 0 to t2. It also means that, you know, the particle travels for a time equal to t2, all right, from this position to reach the ground, okay. So it works both ways. It's both t1 plus t2 equals to the time of flight, and at the same time it crosses the same height at a time equals to t2, okay. Alright, if you have understood this particular discussion, now the next part is very clear here. That is, we know that t1 plus t2 is supposed to be the total time of flight t. And another information that we need, that we want right now, is to just find the height h, which is nothing but the area of this a1. So how much is that going to be? You know that this position, this OB, right? Area of that A1 is supposed to be half OP plus PQ into T1 because it's a trapezoid, and OB and QP can be just added up. So we have half OB is, let's say, the initial velocity U plus PQ. PQ is the velocity at this position, let's call it as U dash, into time t1. So we know that basically it has taken a time t1 to reach this position here. Therefore, I know the velocity v is supposed to be uh, v equals to u plus at, and in this case the a is minus g into t1. So I can substitute in place of u dash u minus gt 1 into t1. This is going to be your area. So it's half 2u minus gt1 into t1. Now, what is the value of u? I know that because the total time of flight is capital T, and I also know that the object reaches the topmost point at a time of t by 2, right, which is the time of flight by 2. So we know that u, if I the value of u becomes 0 at the topmost point, right? So if I use the same equation to get the velocity at the topmost point, I get 0 equals to u minus g into t1. In this case, the time t after which the velocity becomes 0 is capital T by 2, which is t1 plus t2 by 2. Which means u should be equal to g by 2 into t1 plus t2. Let me just substitute here. So 2u should be equals to g times t1 plus t2. So half, in place of 2u, I'm going to substitute gt1 plus gt2, and I already have minus gt1 whole into t1. So gt1 gets cancelled. So I have here half gt1 t2. This becomes my area of this trapezoid. Right, guys? So therefore, my displacement of my height h here should be the same as half gt1 t2. Right? So we have basically used the visualization with the graphs here to understand about this 1D motion, which is very crucial even to the 2D projectile motion. So similarly, suppose I have a projectile motion where I throw a block here like this at an angle theta, and let's say this projectile crosses a given height at first instance time t1 here, and later instance it crosses the same height, right, vertical height, at another instance which is at time t2. Now the total the height h, this height h which it crosses can be given as half g t1 t2, right? Because in a sense that a projectile motion, any two-dimensional projectile motion, when you look at it from, when you project it onto a vertical space, it behaves just like a simple vertically projected object, right? So the same equations would still apply for the y direction velocity u sine theta. If you call it as uy, the same equations would apply here, and you could get the same answers. All right, thank you guys.